Hello everyone, this is Chunjong Park from the University of Washington. In this talk, I will introduce our work on the design and evaluation of a mobile system for rapid diagnostic test interpretation. Testing for infectious disease has become more important than ever. We're still living in COVID-19 global pandemic. Accessible and accurate medical testing sets a ground for public health policies to effectively and promptly control the disease. Within the past year, you have probably been hearing a lot about testing for detecting COVID-19. There are PCR tests, antigen tests, and other mechanisms. One such test format that is particularly conducive to rapid assessment in low-resource settings is the lateral flow rapid diagnostic test, or RDT. Rapid diagnostic test is a convenient way to diagnose various infectious diseases in point-of-care settings. By putting a small amount of biological samples such as blood, urine, and nasal swab into the RDT and waiting around 20 to 30 minutes, RDT shows the result as a visual lines. It costs around $1 and it also has a fairly high accuracy in diagnosing various diseases. In low-income settings, RDTs are widely used for prompt treatment and early control of the disease. In high-income settings, these are used for easy and quick screening at home. RDTs are intended to be easy to read and interpret. If a person has a positive test, multiple lines should appear in the result window. However, some of these lines can be faint due to low viral concentrations, so novice users may struggle to reach the correct diagnosis. Previous work found that only 54% of the participants were able to interpret the test lines correctly, with the most common mistakes being failure to read the faint positive lines or identify invalid results. These failures could lead to fatal consequences, such that patients could be mistreated or left untreated. To this end, we propose RDTScan, a smartphone-based RDT reader, since a smartphone is already ubiquitous in high-income settings and becoming more widely used in low-income settings as well. RDT scan should provide high-quality images without relying on additional attachments to the phone for wide deployability. To do so, RDT scan performs real-time quality assurance and guides users through taking the high-quality images. And using the high-quality image, we aim for comparable interpretation accuracy to human experts. Let's take an overview of how RDT scan works. It first configures camera's auto adjustment with respect to RDT that will be placed at the center of the frame. Then it checks for brightness, blurriness, position, and orientation. The results of quality checks are shown to the users so that users can follow the instructions to capture RDT images. Once it's captured, it goes through a series of image processing to make the RDT results more visible. From here, I'll go into details of each component. We compute the sharpness of RDT image using Laplacian operators. If the variance is low, there only exists non-edges, which means it's blurred. If the variance is high, it includes both edges and non-edges, which means the image is sharp. For brightness, we compute the histogram of an incoming frame. We check for the clipping at the highest values for overexposure. If the peak is located at the low brightness values, the image is underexposed. For size and position, we use SIFT feature-based matching to locate RDT. Compared to the data-driven approach, it only requires a single reference image, which is better for extending RDT scan to different types of RDT. With the detected RDT in the frame, we check whether the RDT is sizable and located at the center. For result interpretation, we first convert RGB images to HLS color space, where L channel represents brightness. We then compute histogram on L channel and apply contrast-limited adaptive histogram equalization. Then we detect trough in the result window, which represents visible lines. Also checks whether the line has the correct color for test and control lines. With that, we evaluated RDT scan in wet lab to confirm that RDT scan was performing accurately and was able to detect faint lines. I don't have time to talk about this study in detail, but the most important finding was that RDT scan's limit of detection is comparable or even better than human experts. Please look at our paper for more details. We then evaluated RDT scan to address these two research questions. First, how well does the capture perform in the wild? Second, does the non-experts with RDT scan achieve comparable accuracy to experts? We conducted 2 deployment studies. In Australia flu study, we recruited patients with flu-like symptoms, and they self-administer flu RDT and use RDT scan for result interpretation. In Kenya malaria study, we recruited 6 community health workers who administer RDTs for malaria patients. And the difference is that the community health workers would use RDT scan multiple times, whereas in Australia flu study, patient only uses RDT scan once. In both studies, RDT scan shows fairly high capture performance. Australia flu study has a bit lower capture performance. It is because participants has more diverse demographics, where older population shows a bit lower capture success rate. Also, there is less chance to learn how to use RDT scan over time. For interpretation performance, RDT scan in both studies shows comparable accuracy to experts' interpretation, and also reasonable performance compared to the ground truth. In summary, we built a mobile system for RDT interpretation, which guides users to capture high-quality RDT images and accurately interpret RDT results in various settings. Our work is open sourced at GitHub. If you're interested, please visit our repository. Thanks for listening to my talk, and I'm happy to take any questions.